So I changed the title of my talk to what I truly believe, that the Paris Climate Agreement is our last best hope to avoid climate catastrophe. And I'm going to talk about these 5 topics in a fairly super fast manner, and I'm not hiding anything here. You'll see these words over and over again. I also want to note that the material in this talk comes from 2 sources. One is we recently published a book called Paris Climate Agreement Beacon of Hope, and we did it by using resource funds from our sponsor NASA such that it's available for free via open access. So you can go to this website, parisbeaconofhope.org, which I know is kind of low, so people probably can't see it. Anyway, if you just Google Paris Climate Agreement Beacon of Hope, you'll find it. Book's available for free. I also was a review editor for the National Climate Assessment that came out this month, and so I'll pull a few items from that. I also just want to stress that I'm sure everyone in the room knows that climate is the average of weather. I can't resist showing this slide, which shows the temperature anomaly observed 5 days ago in our region. So as everyone who lives here knows, we got pretty super cold very fast, but if you look at the rest of the world, this is the difference in temperature relative to a climatological mean. Most of the rest of the world was warm at the same time, and what of course happened here is that the air from the polar region, the so-called polar vortex, came down almost perfectly over the North American continent, and it made us very cold, but the rest of the world is still warm, and so there was nothing of climatic significance that occurred the other day. My group is very proud of this image, which is the Earth's climate history over the last 500 million years that we put together to try to illustrate several very important points. First off, what's shown on the top are estimates of the temperature anomaly relative to pre-industrial over time, and each of these panels called era are different time intervals. So the first one is the last 1,000 years or so. So this is the famous hockey stick, but now shown on a much smaller scale of CO2 and temperature. If we go back, we have the glacials, which were talked about earlier. And during the ice ages, we could record CO2 from air bubbles. Back in time, there were indirect ways to infer CO2, basically looking at fossilized plants and their isotopic composition. 2 big points here. One is that temperature follows CO2. No surprise. And the other is that CO2 was once much higher than today. Here we're at about 400, so geologists truly believe we're once much higher. Of course, we're once much warmer. And this is the CO2 that got buried, the carbon that got taken up by trees, and the trees died and got compacted, and there weren't bacteria to decompose the trees. And this is the carbon that we're now pulling out of the ground, and it's in our vehicles. So it's a fascinating story that we tried to put together in one picture. Now, fast forwarding to modern time, I'm going over a lot of Earth's climate history really, really quickly. I really like this plot as well, because this is one of the numerous lines of evidence. Again, I don't have to convince anyone here that humans are responsible for the centennial rise of CO2. What I'm showing here are the difference between CO2 measured at 2 research stations, one in Hawaii, one in the South Pole, just the difference. And then plotted on the x-axis is an estimate of how much humans release carbon. Now, in everything I'm going to show you today, or nearly everything, we do it in the policy-relevant metric of gigatons of CO2. Often you hear it in gigatons of carbon, so you convert between gigatons of carbon and gigatons of CO2 by multiplying by 44 over 12. What we see here is a compact, near-linear relation. As we release more CO2, the hemispheric gradient of carbon in the atmosphere is growing, of CO2 in the atmosphere, and that's of course because we're releasing it in the northern hemisphere where most humans live. So this is one of the many lines of evidence that we have put together to try to convince the skeptics that humans are responsible. Now, My group's specific contribution to this is we've devised a model. I'll show you model equations at a certain point here, but I'm trying to minimize our equation. This model was featured in the recent National Climate Assessment for the Detection and Attribution chapter. And basically what we try to do is calculate how much variation in the output of the sun, how much volcanoes, and how much natural variability, and most importantly, how much humans have caused temperature to change over time. So the black are observed temperature. The red is a model. The model is the sum of what we call the rungs of our ladder. Note they have different units here. So our units are the same, but the tick marks are spread apart differently. So the sun has a small effect, the 11-year solar cycle. Volcanoes cause a temporary cooling. Now the human component is composed of two aspects that I'm going to get into in great detail. Greenhouse gases that warm and suspended particles or aerosols that cool. So we helped put this together for the climate assessment, showing that humans are responsible for global warming. Okay, you haven't learned anything new yet, I'm sure. Now I'm going to get a little funny here and talk about the overview of climate negotiations in a way of two superheroes and one villain. So let's see how this goes. The two superheroes are Presidents Obama and President Xi, because in 2014 they got together and had a unilateral agreement that the US would agree to peak our greenhouse gas emissions. Actually, it's 26 to 28%, so 27% below 2005 levels in this year. And China would peak emissions by 2030. Obama was in China when this was done. This fed in directly to the Paris Climate Agreement. And the Paris Climate Agreement, as I'm sure you all know, has an intent to limit temperature increase to 1.5 degrees above pre-industrial. That's the goal. But the upper limit is 2 degrees. And this is what the folks who negotiated this wanted to set forth, because climate catastrophe begins to happen when we exceed 2 degrees. And then the countries submitted pledges of how they're going to do this. If you can see this, we have unconditional or promises from the developed world and conditional or contingent pledges from the developing world. They generally extend to 2030. Okay, I'm telling a story, and our story has a villain. Who's the villain? What did you say? Trump. Nope. And I'm serious. The real villain, at least in my opinion, is the US Senate. And here's why. In July of '97, a bipartisan bill put forth by Senator Byrd of West Virginia, Democrat, Senator Hagel of Nebraska, Republican, passed 95 to nothing, not even a single vote of protest, saying that the US would not approve any regulation to limit greenhouse gas emissions. You can't read this unless specific scheduled commitments to limit or reduce greenhouse gas emissions in developing countries, so China was part of it. This was 6 months before Kyoto. When Kyoto was negotiated, it was dead on arrival. And it's never changed. Now, this is hugely important for today, because when Paris Climate Agreement was negotiated, the State Department, under the direction of President Obama, made it sure that it was not going to be viewed as a treaty. Now, people criticize Paris because it doesn't have any teeth. There's no punishment. It's just promises. But that was done in a very conscious way by the US negotiators, because at the time this happened, the Republicans controlled the Congress, and it would not get congressional approval. And therefore, our present president can change it, because it's a presidential decree. Now, to the Obama administration credit, they did something very clever. The date at which it can be changed is 4 days after the next election. So we're committed to it by law until 4 days after the next election. All right, so due to the power of the internet, I got a picture of what the US Senate looked like on July 25th, 1997, at the day this vote was taken. You want to see it? All right. Eventually, our Congress must show leadership. Now I'm going to talk about the work my group does in climate modeling. And there are going to be a few surprises here. So first off, This is a chart which many of you are familiar with. This is the radiative forcing of climate straight out of IPCC. As you all know, CO2 is the dominant anthropogenic greenhouse gas, and we have estimate of how much more heat is trapped in the system. As you heard earlier today, it's globally, you multiply it, it's like 400,000 Hiroshimas. I don't remember, was that every day or every year? It was a huge amount of energy multiplied globally. And we know this pretty well. The sticking point is what I've circled. Aerosols, particulate matter that humans release that reflects sunlight. And we know they cool, but they might cool a lot. This is an error bar. They might cool a little. This is our best estimate. This is what aerosols do by themselves. This is how aerosols mess around with clouds. We don't know what this really is. And this is the beginning of the problem in trying to predict the future. Now, interestingly, when I put this all together and grind the numbers, the net radiative forcing climate's a little bit bigger than CO2, but the real problem is the error bars grow tremendously. And as we'll see, that turns out to be quite important. The other part that I'm going to tell you about, and I know this is hard for people to digest, but I'm going to do the best I can to quickly explain it, is that when we take a look at the climate models that are being used primarily by IPCC, the large global climate models, this is CMIP-5, the Climate Model Intercomparison 5 project, we see that they tend to warm too quickly. Now, this figure, which you can't read here, is 1125b from IPCC. So chapter 11 of the most recent IPCC report took a pretty critical look at the models. And they concluded that the likely range of warming over the next 20 years or so is marked by this trapezoid. And this was their back of the envelope attempt to reconcile the true climate record shown here and the climate record as projected by the large models, which tend to warm too quickly. And I could spend a whole hour talking about this. The bottom line is we think the climate models have cloud feedback being positive and too strongly positive. There are many papers that have been written about it, like this list, that also tends to point to the fact that the climate models warm too quickly. Now, these are climate models that do so many things. They calculate rain, flooding, droughts, ice sheets. They're fantastic for trying to plan. What my group is doing is very simple. We're only looking at global mean surface temperature, trying to account for that. But what we're going to see eventually is that we can still do some very powerful science, at least we think, with a simple approach. So let me tell you about two possible futures. This is the CO2 that underlies what the climate models call RCP 8.5. This is one scenario that all the climate models run. And I'm going to call this climate catastrophe. Another scenario is RCP 4.5, and the numbers are the watts per meter squared radiative forcing of climate at the end of the century of these scenarios. In this one, CO2 never reaches the magic number of 560. 560 is twice pre-industrial. And then somehow methane levels off and falls. That's RCP 4.5. There are two other RCPs, but I'm going to focus mainly on 4.5 and 8.5. I'll come back to RCP 2.6 in a moment. So all the climate models run these. And let me return to aerosols. So the big problem with aerosols is the following. All right, let me describe the chart first. This shows how much radiative forcing of climate we get from the RCP 4.5 due to CO2, as you've heard repeatedly, the most important human greenhouse gas. Methane and nitrous oxide aren't doing much in this scenario, and we know these fairly well, but here is how much aerosols have cooled. And so here we begin to have a problem, because we could have had a lot of cooling due to aerosols, or we could have had very little cooling due to aerosols, and we don't know what the truth is, and the climate models don't know what the truth is, and as you'll soon see, this interferes with our ability to precisely predict future warming. So what my group has done is built what we call the empirical model of global climate. And this is, I only have one other slide with one equation on it. So what we're doing is we're fitting. We're fitting the observed temperature record with our model. Here's a simple set of equations that describe our model. And then this is run, I is the number of month. So we minimize a cost function. Now we explicitly account for heat going to the ocean, which you had heard about earlier today. We have all these other parameters in here, what aerosols do, what land use does, volcanoes, sun, and all that. But the problem is that we have two factors that counteract each other. One is we don't know aerosol radiative forcing. See, aerosols may have offset a lot of greenhouse gas warming. And if they've subtracted a lot off, then this is my climate feedback parameter. This actually has to be fairly large to fit the climate record. Or aerosols may have done nothing. They may have masked very little of the greenhouse gas warming. And if that's the case, this number is a lot smaller. And what I forgot to tell you, so I'll go back, is the aerosol radiative forcing is going away. And it's going away because of a completely separate community, the community of public health and air quality. So right now, actually, the largest emitter of sulfur in the world, which is a precursor of aerosols, turns out to be India. They just passed China because China is scrubbing the sulfur out of their coal plants, and India is not yet doing that. And New Delhi is totally in the news for terrible air quality. Okay, so what my group does is we assume that whatever climate feedback occurred in the past will continue in the future because we don't really know what it is. And so herein lies the problem. The next 3 slides are rather important. So what I'm doing is I'm fitting the climate record. And in this model, for those who actually know the details, I have the Atlantic meridional overturning circulation in our model, which is driven by salinity in the North Atlantic. And in this world, aerosols have offset a lot of cooling. So I really see aerosols showing up. I'm not going to get into the numbers. I'm just going to say that in this world, if I assume that the 2 feedbacks that we think we understand, the water vapor feedback and the lapse rate feedback, if we really know what they are, in this world, cloud feedbacks have to be strongly positive, or clouds and surface albedo. And then when I project forward, and this is all using RCP 4.5, I exceed the Paris upper limit. And this is a possibility. Another possibility is that aerosols have offset some of the greenhouse gas warming, but not a huge amount. And these curves are multiplied by the climate feedback. In this world, I lie in between the Paris goal and the Paris upper limit. And I also conclude that cloud feedback is positive, but only slightly positive. To make matters even worse, I have another world where aerosols haven't done anything. And remember that chart had those error bars near 0. That's a possibility. Aerosols may not have done much. In that world, I infer that the cloud feedback has to be negative. And if it's negative, it'll continue to be negative. And here, I actually can limit global warming to 1.5 degrees by getting my greenhouse gases on RCP 4.5. And this is at the heart of, we have to make policy with uncertain forecasts. So in this world, in this plot, what I'm doing is showing a probabilistic forecast of future warming. And I will eventually explain what underlies this chart, but I want to first explain the colors. The colors mean that if greenhouse gases follow RCP 4.5, that we believe that the human component to global warming will at least follow this blue line. We're certain of that. We think we are. The most probable outcome is the white line in the middle. And then we have a small probability, but it could happen, that we would follow one of these extremes. Here's the Paris upper limit, the Paris target, and here's what IPCC thinks will really happen. Now what I'm going to do is I want to explain the weirdness in this plot, because I have data that jumps up here and then boom, my line comes down. I want to explain this because this white line is our best estimate of what humans are actually doing. So let me explain. I'm going to take the colors off. This is just one of my realizations of the model. This one for RCP 4.5, RCP 8.5. And the model was trained on data, well, when we published our book, it was trained on data that stopped at the gray, but we still had lines that were almost identical to this, because this big burst in temperature was due to a natural variability called ENSO, the El Nino Southern Oscillation, which if I'm asked questions about, I'll be happy to explain. Now, so our model was trained to data out to this point, but we get nearly identical results if we train to 2015, as you can see in our book. So since this time, let's look at what temperature has done. It's gone up a little bit. This is from the CRU in East Anglia. Global mean surface temperature deseasonalized. Now we're outside of our trapezoid. We're still outside of our trapezoid. We're like, what's happening here? And then boom, boom, the months are changing. And just the other day, CRU posted September. We're back down. So again, we think this red line is our best estimate of how much global mean surface temperature will rise if greenhouse gases follow these two different trajectories due to humans, but on top of that is all kind of variability. All right, next I'm going to show how we get our red, white, and blue colors. So when I described my model to you, I had two key parameters I tried to highlight. One was the climate feedback, which is shown here on the y-axis, and the other is the x-axis, how much aerosols have cooled climate. And it turns out that I can fit the climate record for a wide range of combinations of these parameters. Now, what I'm showing here, we call this our ellipse plot, although it's not quite an ellipse. What I'm showing here is the region of model space where a physicist would say, I have a decent fit to my climate record. For those, well, I'm sure engineers use reduced chi-squared, so we use the reduced chi-squared metric. This is where I can get a reduced chi-squared of 2 or less. So the best fits occur in the middle here, but anything within this space we call a reasonable fit. Okay, so this is a very important plot. Now, the colors are how much warming I'll get at the end of the century. So if aerosols have offset a lot of global warming due to greenhouse gases, well, I need a strong climate feedback to explain the climate record, and when aerosols go away, that climate feedback stays and global warming is unleashed. Aerosols have masked a lot of global warming. It's not going to be pretty. On the other hand, if aerosols have done very little, I can fit the climate record with either, actually a fairly large range of feedback parameters, some of which are positive, some of which are negative, and warming won't be nearly as bad because there's nothing to unleash. Aerosols haven't done much to mitigate global warming, so when they go away, nothing's really going to change. I can only fit the climate record with small feedback. Now, this plot here on the top represents a statistical sampling of an ellipse plot for every year. This one's for 2100. So all we do for the 2100 is we look at all the points within this ellipse plot and we calculate what we call probability distribution function. So what fraction of the points are above a certain temperature, and we do weight them by reduced chi-squared. So the better the fit, the higher the weight. So it's 1 over reduced chi-squared. Okay, and so what we see here, and then we just we do it for each year along the way. So the white line is our most probable outcome, but we could be anywhere from below Paris to way above Paris because we can't rule this out, but this is a possibility. On this chart here, I'm showing the probability distribution function only in 1 year, 2100, and the way to interpret this plot, the peak is at this where I'm pointing, and the temperature at the peak is somewhere between like 1.1 and 1.2. So this is our most likely outcome. The temperature will be in this range. It could be in this range. So our most likely outcome is that we'll be below 1.5 degrees, but that's not particularly comfortable, half above, half below. But then our probability distribution steeply comes down so that most of our model realizations lie below 2 degrees. So these numbers represent the area under the curve that's to the left of the Paris goal and the Paris upper limit. And then here are the large climate models, which again, a lot of the community thinks warm too quickly. And I'll get back to this at the end of my talk. Now, if you've stayed with me, I just want to point out that what I've shown here is a physicist's approach to doing it. A physicist would say, I'm just going to take all my model runs and I'm going to use the principles of physics to average them. There's another way we can do the averaging, and that's to put on our climate scientist hat. See, the climate scientist says, I have information about where we actually are here. And so the IPCC thinks that they can make estimates of what aerosol radiative forcing is. Now, we don't know it well, but IPCC says the best estimate is about minus 0.9. It's likely to lie between these two numbers, and it's almost certain to lie between these two numbers. So what my group does is we fit a Gaussian to these estimates, and we redo the averages. So this is the first way, and watch how it changes. Okay, so now this is the physicist's way, this is the climate scientist's way. The climate scientist says, I actually have information along here that I'm going to use. So the physicist would weight every point here the same as every point here, but the problem is I got lots of points here, and I have very few here. The climate scientist says, no, no, this point should have the same weight as this point, because they're both unlikely, and it's just a nuance that you can fit it with a wider range. I prefer to use this one for policy, and now you see our PDF, our probability distribution function, has more overlap with the CMIP5 models. We still think that we would have a 72% chance or a 3/4 chance of staying below 2 degrees if we could put greenhouse gases on RCP 4.5. And that is our message, that our modeling approach indicates that RCP 2.5 should still be on the plate as likely being the 2-degree warming pathway. So I know that a lot of the climate community does not agree and thinks we need to go to RCP 2.6, but there are the folks who run the large models and the folks who look at data. Most of the folks that look at data have reached a similar conclusion that I've shown. Now, if we run RCP 8.5, we get this projection using the physicist approach, and we get this projection using the climate scientist approach. We need to not follow RCP 8.5 or we're going to be in trouble. All right, the last slide I think I'm going to show in this segment of the talk is for a new item coming down the pike. It's called the Shared Socioeconomic Pathways. For those who actually know about the greenhouse gases and all that, in the RCPs, 4 groups were assigned to come up with 4 different scenarios, and they were told, give me 8.5 watts per meter squared by end of century. Give me 6. Give me 4.5. Give me 2.6. They were told that. The SSPs are a totally different way of looking at it from the bottom up. If we do this, composting. If we do that, coal and natural gas. If we do that, nuclear. If we do that, solar and wind, what will the greenhouse gases give us? And whatever radiative forcing you get, you get. So these are being developed. We can start playing around with them. I'm just showing one of these here. These are the CO2 scenarios that are published so far for the SSPs. I've highlighted the 3.4 watts per meter squared one, and here's our ellipse plot. We actually call this the Patriots plot because it's red, white, and blue. It's so patriotic. Here's our PATS plot for 3.4. Here's the climate scientist way of looking at it. Here are the two together. So, you know, if we can get greenhouse gases on the 3.4 watt per meter squared pathway, we would have a really good chance of staying below 2 degrees warming if we're a physicist. And if we put on our climate scientist hat, we still have a pretty good approach. And let's go back and look at these. This is CO2, again, falling below 560, and methane somehow, some way, coming down dramatically. Okay, so I'm done with the first 3 of my parts. How am I doing time-wise? All right, great. I think I don't even have time for questions or discussion, or I'll get us back on time. All right, so now, I'm going to talk about the Paris Climate Agreement. So I assume that everyone in the world knows that China is the largest nation in terms of greenhouse gas emissions, and US is second. I've done this in units of CO2 equivalent, so it includes, as we've heard earlier, fossil fuel land use. You multiply by global warming potential for methane and nitrous oxide. We're using the 100-year time horizon like everyone else does. What country's third? Louder? India, great. Anybody know who's fourth? Russia. And it varies, Japan is up there. It varies on how you consider land use change and whether you look at methane or N2O. According to our sources, Russia. Now, Of these four, who leads in per capita emissions of CO2? And it's not even close, right? Well, USA, so we're number one. We emit 2.5 times per person, all of us, on average. Well, we have some non-US folks here, but they probably flew here, actually. We got to get renewable jet fuel out there. All right, now this is scary, what I'm going to show next. Here's what it looks like. So Russia isn't far behind. China's catching up. There are more than half of us now, and look where India is. And for the young people in the world, y'all are going to have to figure out how we're going to electrify India and Africa without repeating the use of fossil fuel that we did here in a fair and equitable way, because some African nations are sitting on a lot of coal. India has more people without access to electricity. More people in India don't have access to electricity than live in the United States. And so when people cook their meals in India, it's every day they just buy their food and cook it because they can't refrigerate it. Walt is in the room. Walt made a lot of these plots. Wave at Walt. Thank you, Walt. Okay, so Walt made these plots showing the per capita emission of CO2 over time from the big three. So we're starting to see China move a little bit more. China had plateaued, starting to pop. India is just coming up. And we also love to look at these cumulative charts. These are projections out to 2017. And this is when the US Senate got scared of China. I'm sorry, isn't that sad? The US Senate would not approve anything that didn't put brakes on China in 1997, when we had emitted so many more greenhouse gases to the atmosphere. But it is what it is. Eventually, the US Congress is going to have to take some leadership. But for now, we're doing a lot with states, municipalities, and cities. All right, so Walt is a very valued member of our research team. Walt looked at all of the INDCs submitted. Actually, Walt was in Paris for COP21, and after the INDCs were submitted, Walt and I did not have Christmas and did not have New Year. For us, it was a day and a night. We're working furiously on trying to understand the INDCs in a fastidious manner. So what I'm going to show you now is our hopeful path, RCP 4.5, the one we want to avoid. And this is a projection. This is data on the global CO2 emissions. And this is Walter's projection of business as usual. So it's using, for folks who know the word, it's called the Kaya identity. Looks at population, GDP, carbon intensity of economies. I'm probably forgetting a few things. And it projects out. This is basically the track we're headed on. And here's maps of the world of what would happen if we followed business as usual. So what Walt was able to do is put together a chart showing how the projections of CO2 emissions would change if we actually did all the unconditional INDCs. They're now called NDCs, if we did them all. But here, most of them go out to 2030. And what we're doing here, what Walt's doing in his models, is he's keeping the carbon intensities of economies level after 2030. We call that attain and hold. One of the messages of our book is we have to think long. We have to go out at least to 2060. What Walt's done here is he's improved the carbon intensity of the world's economies in a linear fashion out to 2060, which for many countries is going to be a really tall order. And now we're getting close to what we think is the hopeful line, RCP 4.5. And the last thing that we're going to do here is we're going to actually put in the conditional NDCs. So you could see India changing color. India's NDC is half conditional, half unconditional. Some of the African nations are changing. So basically, we need everything to go after this. Okay, now I'm going to talk about energy next fairly quickly. This is a very important chart showing that we get about only 20% of our energy globally from sources that don't release prodigious greenhouse gases. That's how I write it, because we get maybe a little bit from some of these. And the bad news is that half of that is biofuels and waste, which, as we heard in the response to the question from one of the prior speakers, is really, really a bad thing because of air pollution. Or to Mark Jacobson said that. All right, so this chart shows projections from the US EIA of what the world is going to do for consuming energy from the three forms of fossil fuel, from renewables and nuclear. This is an agnostic forecast. In other words, it's just what they think is going to happen. No changes in policy, not saving the world for climate, just what they forecast is going to happen. A lot of businesses really care about this. Obviously, nuclear is staying flat because of Fukushima. What my group has done is then computed how much CO2 is emitted from the three sources. So liquid fuels, natural gas, and coal. CO2, again, lying between 4.5 and 8.5. Now, this might not look that bad. It might not look like that big of a gap, but it's a huge gap. What we've done in the next slide is we've shown how much global energy, primary energy, not electricity, but energy, much more than electricity, how much we need to get from renewables if all we're going to do is squeeze the fossil fuels down to match RCP 4.5. So we force the fossil fuels to match RCP 4.5 starting in 2030, track it afterwards. We have to grow global energy from renewables to 50% by 2060. Now, some of the rest of the world, or actually a lot of the rest of the world, thinks that this isn't good enough. They think we have to get emissions to follow RCP 2.6. And if that's the case, what you often hear bandied about is CCS, carbon capture and sequestration, which I should have written on this slide here. So the only way that we feasibly could do 90% of our, 93% of our energy without releasing CO2, or greenhouse gases, to match RCP 2.6 is a major effort for renewables and somehow do carbon capture sequestration. In the US, they talk about CCUS a lot. The U is utilization, so trying to actually make product from it. And there are efforts in the Congress to do some of this, usually putting the carbon back out to extract more fossil fuels. So don't get me started on that, but it's happening at that level. All right, my last part is the US intransigence. Let's state the obvious, it was already mentioned several times here. What are we going to do about the situation in the US? And my word is just hold tight and wait for the US to come to its senses. So here's the deal. I had shown this before. This is our whole 9 yards, unconditional, conditional, staying below 4.5. A lot of people are surprised by this, but I'm going to try to back it up. If the US does business as usual, it hardly changes. Okay? Our president, as powerful as he is not going to revitalize coal. The US emissions are on a trajectory down and he can't change it. This is the Kaya identity applied to the US emissions. It's not a game changer if the US does its thing and the rest of the world does the right thing. Of course, the problem is if the US goes rogue and stays rogue, all the money for the developing world is going to be very hard to come by. I'm not suggesting the US should do this. I'm suggesting the world should stay tight. This is if we have an 8-year delay, God forbid, and this is a 4-year delay. Okay, so the reason why the US is not showing up any more than you think it should is the US emissions are going down, leveling off and going down. So let me explain this. This chart was all over the news and Twitter and everything because for COP23 in Bonn, this got released. These are global emissions. Now these are just CO2, so the numbers are a little different, from fossil fuels and industry, not land use change. And it looks like 2017 is going to peak up just a little bit relative to 16. This is actually a paper was published by, you can't read this, but Jackson et al. In Environmental Research Letters just a few days ago. The reason it's popping up a little bit is China is projected to be higher than it was in 16. The rest of the world, other than China, US, EU, and India, is popping up. The US is leveling off according to them. EU is leveling off. India is going up a little bit. Now, what I'm going to show next is going to elicit maybe a gasp from some people because no one ever shows this, but this data is all publicly available. I'm not apologizing for my country's present political situation, but it's not as bad as many people think. What I'm showing here are the actual US emissions of carbon in the policy relevant CO2 equivalents over time. We have come down. A lot of this is, there are various factors: economic, coal to gas, vehicle efficiency, efficiency of our economy. The lines here are the projections of what the US was predicted to do by the very smart people who put the RCPs together. So we're actually doing well relative to the RCPs. And this is all publicly available information. There's no magic here. China is growing more aggressively than was thought back 10 years ago when the RCPs were put together, or 15 years ago. So this is, the circle here is 2005. So this was all meant to be tied to real data. So China's popping. Now China's promise is to peak in 2030. And then India is far below here, and you think, well, US matches this line in the circle, and China does. Why doesn't India? The India greenhouse gas revisions got revised downward by 20% a few years ago, and that's just what happened. We're not sure exactly what happened there, why that is. Now, this goes to 2015. Here's what happened in 2016. And here's our projection of what will happen in 2017. The US is not popping, China is popping. Here's what it looks like for the world out to 2015. So the green line is the line that we think we have to get to. And here's what the US has done relative to the RCPs. This was the Obama administration pledge. This is out to 15, out to 16, out to 17. Okay, so we're trending up. This is our latest estimate of business as usual. So the US business as usual will still keep us below 4.5. Using the Chi identity, 17 peaked up here. It's very important that we get this to come down and stop going up. The rest of the world has to hold tight. This is the last slide I'm going to show with my conclusions here. I just want to again reiterate that at a certain point, the US Congress needs to step up and lead. A lot is happening in the US with states like Maryland and California and a number of other states, with cities and with municipalities. But to really do this right, we need a nationwide renewable portfolio standard. We probably need a carbon tax or a cap and trade. There is a cap and trade that most people don't know about called RGGI, the Regional Greenhouse Gas Initiative, that 9 states belong to, including Maryland. So hopefully we'll see something like that happen for the entire US. In the meantime, hopefully the rest of the world will hold tight. And if there's time, I'll be happy to answer questions. Thank you.
Thank you very much. Thanks for staying late. I heard we've seen a lot of presentations that are probably depressing you, and one of my goals here is to try to give you guys some hope. That's part of the mission of the Climate Reality Project. I'd like to thank the professors here at the School of Engineering for inviting me to speak to you today. And I'd like to tell you a little bit about the organization, the Climate Reality Project, which is what I volunteer for, giving speeches, part of which you'll see today. I also work as a senior campaigner with Greenpeace on their food campaign, and I'll tell you a little bit of work about what we're doing there as well. But I'm here as a volunteer for Climate Reality Project. So first of all, I'd like to thank Ezio Mattiace, where are you? There we are, for we actually looked at our trainee. He was trained as a Climate Reality Project leader in 2013 in Chicago. I was trained this year in Denver, and there's about 3 or 4 trainings every year. One of them, or 1 or 2 of them, are international. And what they're doing is people apply to become a volunteer leader, and then they are trained by Mr. Gore and his staff to give presentations. Of course, we change it, slice and dice it, add to it to make it relevant to different audiences, which we're doing. And Ezio gave the depressing part, which was all of the storms and the data that's showing that we are indeed global. I'm going to do a quick review of that, though I've noticed with the other presentations, we've had quite a lot of that today, so I'll rush through that, because my goal is to tell you about exciting things that are happening in technology with renewable energy and solar and wind and lithium-ion batteries, and how those markets are taking off, but also talk about some of the political energy that we're seeing and the UNFCCC process. Of course, the Bonn conference is going on right now, COP23, and some of the things we're doing locally, because Climate Reality is also starting a chapter network to create local chapters to do more than just speaking, but actually get involved with campaigns. So if you've seen how many people have seen The Inconvenient Truth, the original climate Change back in 2006? Okay, Al Gore's movie. And how many saw the sequel that came out over the summer? Okay. That's usually the hands that we get. Make sure it's coming out on iTunes and Netflix, of course, soon. But that second movie really shows what people like Ezio and myself do, where we're speaking and sort of giving testimony all over the globe. It started, and you'll see in the movie, in Al Gore's barn and his Nashville family home with about, I think, 50 trainees. And we're now up to almost 19,000 trained leaders. And these aren't just, there's a lot of scientists and engineers that are in the group. There are also people like myself, professional environmental campaigners. There are educators, kids, artists, everyone that you can imagine. They're all learning this and trying to find out how to basically talk about climate and climate science. As I mentioned, chapter organizations, there are also 10 international affiliates in different countries that are doing similar things. They try to set up an affiliate after they do an international training. So I'm going to briefly go through some of the stuff that Ezio has gone through, and I'm not sharing it to educate you. You all seem extremely educated here. I'm sharing it to show what we share with the public and the key takeaways, because a lot of time we're talking to people that have almost no baseline of climate science, and that's the goal, is we're trying to give them a baseline. So the first thing, of course, is when you're looking at billions of metric tons of carbon, we're clearly emitting more carbon into the atmosphere at an exponential rate, approaching nearly 10 billion metric tons of carbon presently, and business as usual, we're going to exceed that. And this is something a lot of people know, that we're warming, but also there are three major carbon gases, as you know, carbon dioxide, methane, and nitrous oxide. They all have different durations in the atmosphere and different heat trapping properties. But this is showing, a trend that right now is perhaps flattening if you look at it, but certainly not reversing, which is what we needed to do. If you look at the United States and the breakdown, most of this obviously comes from our energy. Some data, and looking at international data, disputes like the role of agriculture, and I'll get into that a little bit later. But clearly a lot of the focus on all the climate political negotiations and a lot of the policy is on these things, which are basically electric and heat, how we run air conditioning and heat our home, and what's fueling that: natural gas, coal, solar, wind, what have you. And then, of course, transport, how we get from point A to point B. Another thing that we try to let people know is CO2 concentration in the atmosphere. If you track it, and of course this is a calendar, and this is going the years, you can barely read them, that they're in the middle there. But we're showing that we've been slowly, since the beginning of the Industrial Revolution, been increasing the amount of carbon dioxide in the atmosphere. And in recent years, that's where we are now. So we're, and this was said in an earlier presentation, but we're exceeding 400 parts per million of carbon dioxide in the atmosphere. Then we usually show, this was actually a similar thing, but it's actually showing global temperature change. And this is global temperature change. I think this is atmospheric global temperature change. And what you're seeing, of course, is a slow but sure increase. And of course, 1.5 degrees Celsius is the threshold that we're trying to achieve with the Paris Climate Accords and not exceed that. And as you can see, in recent years, the temperature change in the extreme weather is actually sort of going off the charts, as it were. So we're letting people know carbon dioxide increase, temperature increase, there's a correlation. Also, if we're looking at cooler than average temperatures versus warmer than average temperatures, this is NASA data that is looking at the mean temperatures and the deviations from the mean from 1951 to 1980. That's the bell curve that we've had during that time period. And if you look at it over the last decade or so, you're seeing a much, much larger incident of warmer than average anomalies and more infrequent cooler than average anomalies. And extreme temperature events, which we're seeing manifest in terms of wildfires this year, drought. Drought. It now covers 14.5% of the Earth and where the incidents happen. So that's something you show people when they're saying, well, why is it cold during the winter? You're trying to show that there's the difference between weather and climate. Another very clear piece of evidence, which you hear in the news every year, is we have hit 16 of the 17 hottest years on record since 2001, and we probably will do it again this year. That's last year was the hottest ever measured. Does anybody know if we're on track for that this year to exceed? Yes? Yeah, okay. The other thing we try to let people know is if you look, and again, if you're with Ezio this morning or if you get another climate reality leader to speak to your group, we go quite in depth on extreme weather events, but the main things that we go through are storms and what we call megastorms or rain bombs, like the ones that have happened in Texas and Louisiana over the past few years. Extreme temperatures, droughts and fires and wildfires like we've seen in the Pacific Northwest, Los Angeles, and Denver, and then of course floods and mudslides. And the presentation actually has a lot of anecdotal evidence. In fact, one depressing thing about being a climate reality leader is we usually get an update to this deck, all of us, so we can talk about recent events. And I have found myself going to the news to put in events from the 3 hurricanes or Puerto Rico because I can't keep up with the anecdotal storms and wildfires that are happening in a 4-month period. They did that with Pittsburgh, and hopefully with the winter maybe there's a little bit less, but I'm sure next year there'll be more. Of course, global record-breaking precipitation anomaly. We're just getting, of course, more ocean heat, which means more evaporation, more precipitation, and more extreme rainstorms. Hotter years, more fires. There's a correlation, not exact. And of course, from the expanding ocean water, and then of course, polar ice melt. These are the top cities that are going to have risk in terms of population and millions of people affected, displaced, etc. So this is the part. Well, and I think everybody knows what the subprime carbon bubble is. But basically, we have 1,821 gigatons of carbon dioxide burned from 1850 to 2010, really when we started using petroleum for energy needs. And since 2000, that's how much we've burned. And the rest of it was the 160 years prior to that. And of what we've drilled and identified and that we can burn, we have that much more left to burn. Which, of course, if you've been paying attention today, we can't burn nearly that amount if we're going to avoid extreme weather and basically a planet where large parts are uninhabitable. That's what we can burn to stay under 2 degrees. Of course, we're now going for the aspirational 1.5 degrees Celsius, and the UNFCCC is trying to find out measures and rule books to actually adhere to that Paris Climate Agreement that we've had. So actually, that gray circle should be smaller. Which means the rest of it is stranded assets, unless we just ignore whatever policies are coming and burn it anyway. And one thing that that was mentioned at my table when we were trained in Denver was we can't take that red stuff lightly. If we do, don't burn the red and actually don't burn into the gray. We're talking about lots of jobs. Lots of the economy, from our transportation infrastructure to our energy, it's going to have to go through a massive transition. The coal industry, of course, is doing this already. But there has to be smart policies to allow people working in those old industries to find livelihoods in those new industries. I did want to talk a little bit. I mentioned earlier that I work on Greenpeace's food campaign, and I'm happy to announce that we're starting a campaign to address industrial meat and dairy and its effect on the climate. And this is something actually addressed in Al Gore's presentation as well, though he often talks about how climate change affects food in terms of drought and crop yields and so forth. But I wanted to also share some information, which a lot of people don't know, about the contributions of our industrial agriculture system. And I think, Ross, are you still here? We were speaking about this earlier. So obviously, food and heat can lead to all of these different things, and pestilence and floods and too much rain, too little rain, fires. All of this affects the security of our food system. A lot of people don't know this. This is FAO data from, I believe, 2014, I think. But 14.5% of all greenhouse gases, about 7.1 metric gigatons, actually comes from our industrial livestock system. And that is calculated by looking not only at the land that we don't use, or was once forest that has been deforested and taken down a carbon sink to make for things like this, a concentrated agricultural facility, or a CAFO as they're known, where animals are crowded together. In addition, as people probably know, methane, a large part of that comes from the agriculture system that we have, and it comes from the forms of manure, cesspools of manure, cow farts, all of these different things. And so agriculture is something that needs to be discussed between us and between our friends, because even if we solve all of the transportation and energy challenges we have, there's still a big piece that we're not challenging. And incidentally, that 14.5% is about the same as all transport, planes, trucks, and cars in the world. So it's that meaningful of a percentage globally. A lot of people also don't know, I think this is 2014 data. Back then we had 7.3 billion people on the planet, and at the same time, that's how many animals we had living bred for food, which is 67.9 billion. So a huge animal population boom vis-a-vis to feed all of these people. And of course the population will increase, and therefore if we don't change our eating habits, so will the animal population. Also per capita meat consumption, and of course red meat, especially beef, whether it's factory farmed or free range, has a bigger carbon footprint rather, than poultry and other forms of animal protein, though they also have one as well. But the recommended, sorry, the footnote is incorrect, but that recommended allowance for your animal protein consumption is where that orange line is, and this is what, in the different continents, the per capita kilogram annual consumption is. So we're eating more meat than we need to meet, and also there's other places to get consumption. In terms of deforestation, this is just a NASA image. Greenpeace has a forest campaign, and one thing that we're doing, because it was traditionally a deforestation campaign, is we're actually looking at meat consumption patterns and how the phenomenon of deforestation in places like the Brazilian Amazon and the appetite for the meat and the feed coming from places like Brazil are impacting. You're seeing a time-lapse satellite image of the level of deforestation for grazing land and for feed for international markets. And of course, this is taking away one of our key carbon sinks that helps regulate their temperature. Just to put a finer point on it, there's a calculator you can do online. Just Google a global calculator that allows you to put in different inputs and reduce different things to find out what kind of impact we have. And we ran this. Some of the Climate Reality Project leaders interested in this stuff, we're creating some slides and found out that even if the carbon footprint of every other sector shrank to zero, so cars, energy, and whatever, but we just didn't touch agriculture, we would take the entire carbon budget that we have to stay under that 1.5 degree just through that alone. But if you were to, aspire to have sort of a low meat consumption, not a vegan, vegetarian world, because that's probably not realistic, but you would actually have a better chance of getting toward at least the 2 degree Celsius target. So agriculture has to be addressed as well. But anyway, our challenge is everything that we do is contributing to this problem, and we really have to look at sort of a holistic approach to how we live and how we, how our democracies or our governments work, to start taking action on some of these things. And the good news is, this is our Easter Island slide, and so usually this is the part where Al Gore pauses, and we best depressed by all this stuff, and I felt like I can't do this. But actually it gets optimistic after here. So I'm letting you know the Easter Island slide is where we turn the corner. But of course Easter Island is shared because this is one of the examples in human history where a civilization basically used all the resources they had and annihilated themselves. So this is sort of a caveat of a slide. But we have solutions at hand. And we're going to go through lots of solutions actually and lots of good trends that we're having. So first of all, one thing that we should be thinking about or looking for precedents in human history, recent human history, where rapid adoption of new technology changed. So who can give me an example of a big technological change that's happened, let's say, the last 40, 50 years, our lifetime, or maybe my lifetime, maybe it's less for you, but cell phone. Interesting, okay. Well, so what we're trying to let you know here is there's a lot of predictions that are made when new technologies come online, and as a general rule, depending on the technology and the cost of that technology and the interest, they tend to be wildly off. So in 1980, AT&T commissioned a study and said that cell phone usage would be about, in the year 2000, and I think back in 1980 there might have been the big car phones, but that's about it, 900,000 users. I think we were more than that in 2000, but let's check. Yeah, it was 109 million, so they were off by a factor of 120. And what are some reasons why people tend to get these predictions of new technologies off? Just throw a few out. Anyone? Infrastructure. Oops, sorry. Yes, thank you. Sorry, I have one out of slide thing. They were way wrong, and yes, let's talk about some of them. So one, these technologies tend, for different reasons, so with the personal computer revolution, or maybe the internet revolution, of course the mobile phone hardware, and then mobile internet evolution, cost drop. The cost of a chip drop, but also the quality improved dramatically. So that's Moore's law, right? Moore's law in terms of chip performance, cost goes down, performance goes up. And then also in terms of international adoption, a lot of places that didn't have landline never got them. So if you've traveled to Africa or maybe the Middle East, then you've noticed that people don't even need landlines, and the mobile phone, maybe not the smartphone, but a feature phone is something that they use because they just skipped the old technology. And we're looking for those types of trends now. So let me go back to my out of place slide. Sorry, here we go. Okay, so here's mobile phone subscriptions. And this is the trend that I'm talking about. In developed countries, of course, they were introduced, all of the nice, expensive iPhone 3s, 4s, 5, whatever, all the way through the 10s are there. But it's the cheaper, the Nokia phones, or the Samsung phones, or the feature phones that really exploded. And that's really where mobile phone subscriptions took off. Sorry. Okay. All right. So let's talk about some new technologies that are coming online now that are showing these trends. So one thing that we have, of course, is the LED light bulb. How many people have regular incandescent light bulbs in their house, or how many people don't know what kind of light bulbs they have in their house? Okay. Does anybody know the difference between an incandescent light bulb and an LED? Yes. What? Yeah, one is more efficient. Yeah, definitely more efficient. It emits less heat for sure. It also lasts a lot longer. But according to these trends that we were talking about, also the price has gone way down. So if you go into Home Depot now, for example, and you look at the light bulbs available, most of them are LED. And in fact, I just bought a new home this year, and the first thing that I did is I went through and I said, I'm going to change all these incandescent light bulbs from the previous owner to bring down my energy bill. So LEDs have now reached critical mass where they are the preferred lighting, at least in home lighting, and that's having a big effect, of course, on the growth of the LED market. We're basically now, in 2020, it looks like we're, or will be, I don't know, we're about between 50 and 75%. Maybe at 50% now, but the projection is that basically almost the entire home lighting market will be LED. I don't know if that actually includes non-residential like businesses, but the trend is clear. It's cheaper, it's more efficient. It also encourages energy efficiency and makes your energy bills more efficient, and therefore they're going to get the market share. Let's look at wind. So the same thing that we're seeing here in terms of, this is euros per megawatt hour. and the cost that it used to cost back in the 80s, and that has consistently gone down. And of course, this shows megawatts deployed because of that cost. So we're now approaching 1 million megawatts of onshore wind this is global data. And conversely, we're seeing wind energy capacity starting to increase exponentially, I believe somebody said. These trends seem to happen, and people are not really gauging the sudden price falls that we're seeing and the sudden adoption. And so it's sort of market forces are sort of dictating the direction that things are going in a way that isn't predictable, but is kind of positive, because these are not clear geometric trend lines, but these are trend lines that are promising to keep growing. So if you look at wind, this is a projection, remember back to our AT&T example, worldwide wind capacity will reach 30 gigawatts by 2010. Okay, that was what we thought in about 2010. How many people want to guess how much we exceeded that estimate in 2010? Anyone? Okay, 10 times. Good guess. 16 times. This is in the United States, wind energy capacity. And this is cumulative wind capacity in megawatts, growing. And these are some examples. I'm sure if you drive across the country now, you're starting to see more things like this. I have family in California. When I drive through Indio, there's just tons of wind turbines out there. And in places you wouldn't expect, like Texas, this is becoming one of the largest growing new energy sources coming online. And so Washington State, for example, produces enough wind to power 746,000 homes just through wind. Overseas, of course, onshore wind is becoming viable in many markets like Denver, where sometimes entire days they have all of the nation's electricity needs powered by wind. So if you looked at wind itself, it could supply worldwide electricity consumption 40 times over, potentially. And right now in the United States, we have about 84 gigawatts of wind installed for 25 million homes. Solar. So who can tell me basically what's happened in like the last 3 to 5 years in terms of the cost of solar and what forces were driving that? Okay. Well, solar has come way, way down, and part of it had to do with the fact that China saw a market but produced such large amounts. They basically flooded it and made solar cells the cheaper that it's ever been, where it was very hard to compete if you were a solar manufacturer. But what that did is that stimulated the market for solar installers, and it also made solar very, very cost competitive vis-a-vis other technologies, especially natural gas. And the interesting era that we're entering now is, while natural gas has been a bridge fuel and it has contributed to U.S. energy independence and a drop in the price of oil, the new technologies are actually showing that they potentially can be cheaper. Of course, if you have natural gas over time increases, and those increases in price and excavation are passed on to the consumers, where you don't have that same phenomenon with solar or wind, because it's not a finite resource, a renewable resource. You know, the sun doesn't burn out. And so solar photovoltaic installations worldwide now exceeding 300 gigawatts. And you're starting to see evidence of that everywhere. And of course, in the United States, it's not nearly as high, of course, but there's been growth because the market forces are encouraging a serious look from really progressive utility companies like Edison in California to put a large amount of renewable energy in their mix. In addition, many states, I think over certainly over 30 in the United States, have mandatory renewable portfolio standards on the books, which forces the utilities to have a certain mix that includes renewable energy. But also, and in my case, I'll get into it in a little bit, the cheap cost of solar has also driven down home solar, so the price of actually having your own home solar system has gone down dramatically. So solar energy process, same thing. 2002 projection, it would grow by 1 gigawatt per year in 2010. Anybody? Did we hit that estimation? No. How much did we exceed it by? Okay, you're catching on. No, we're going to be 17, but keep that idea. 17 times. That really shows. Oh wait, sorry, I messed that up. Sorry. There's actually a reveal. There's like. Yeah, so the 17 times actually refers to how much was done in 2010, the same year that they had. But of course, it's 2016, and so we're seeing an exponential growth rate. So that's what we have now. And so you're starting to see this. How many people are kind of noticing in their lives or in their travels just more solar in different places? Show of hands. Just where are you seeing this stuff? Arizona? Okay. This, yeah. Where else? California? Yep. There's big arrays like this you're seeing in places like Nevada and California, but I'm actually seeing it in Virginia. Like I'm a cyclist, and I was going through on a race recently, and I saw a number of farms actually that have actually converted their farms to partial solar generation. I guess they have some sort of agreement to produce for the grid, but it's also becoming something that you are seeing as a sort of a revenue diversification approach to landowners. In addition, my grandmother lives in Phoenix, which is a very deep conservative area. But I swear, in her retirement community, every fifth or sixth home has a solar panel, and it's simply a matter of economics for those people. It's not. They will buy solar regardless of whether they believe the climate science or not. They just think it makes good economic sense, which is fine. That's what the Vatican looks like. Since I'm at Catholic University, I'm going to hang on this slide just slightly more, a little more time. Okay, good. Chile. And Chile is kind of one of those markets where they have all of the right conditions for solar to really take off. This is a 100 megawatt farm in the middle of the desert. So this is the end of 2013. They had 11 megawatts online in Chile. The following year, they had 402 megawatts online. And the end of 2015, 848 megawatts. And in process, here's how much solar is forecasted to be built in Chile. I get dizzy just looking at this one. So about 13, let's see, there it is. This is projected. In other words, these are solar generating farms already contracted to be built within Chile. 13.3 gigawatts. So new generating capacity, this is kind of where investors are going to start looking at where to put their money, where they're going to see the most growth. So obviously, when you look at back in 2009, a new energy generating plants that were coming online, there was about parity between fossil fuel, coal and natural gas, and renewables. 2013, the picture starts changing. And this is new generating capacity, just to be clear. This is new stuff coming online. And then 2015, the trend is continuing. So a lot of people are saying because solar and wind are cheaper, because we're getting a more integrated grid, and because there's just not really the political will, and there's a lot of political pressure to not invest in new technologies, or sorry, in older technologies, the newer technologies are seeing a great increase in market share. And this is the similar thing, the forecast, new capacity coming online in the US in gigawatts by 2030. And there's nuclear. Nuclear, relatively clean, but also extremely expensive. Okay, everybody has this technology. They're looking at it now if they're bored by my talk, but the lithium-ion batteries, of course, one thing about solar, and if you own solar, you know that if it's a cloudy day or if it's at night, it's not that helpful. But we're now getting into technologies where we can sort of time shift that solar energy to when we need it. So this is the cost of lithium-ion batteries, cost per kilowatt hour. And we're seeing dramatic drops in the cost of that storage. I'm sure there'll be environmental impacts once that takes off and we figure out where we have to get all of this lithium. But what we're seeing is an explosion in the U.S. energy storage market, and this includes phones, electric cars, home energy storage like Tesla's Powerwall, and its competitors. And then, of course, utilities trying to find ways to build their own lithium-ion infrastructure to also provide electricity should there be an emergency, or should their renewable infrastructure go down for whatever reason. So Bloomberg said a couple years ago, basically, solar plus batteries could be a dramatic shift in human civilization, because it simply means that we're going to be able to, if we have enough capacity online, have a world where we're having basically, I think Elon Musk calls it the great nuclear reactor in the sky, the sun, but be able to distribute and to store that energy efficiently for our energy needs. How many people own a hybrid? Okay. How many people own a plug-in hybrid? Good for you. How many people own a pure electric car? All right, great. What model do you have? Yes. Oh, wow, impressive. So one thing that we're starting to see, and again, we should say that the electric vehicle market is still very, very small compared to the combustion engine market. But even since I've been trained and we're getting these slides, amazing things are starting to happen in that market as well. So obviously, if you're familiar with Tesla, you know that they came out with the Model 3. The Model 3 is basically the affordable, not for me, but the affordable mid $30,000 new car that has a range, I believe, of just north of 200 or 250 miles before you get your next charge. And this is supposed to be their mass market vehicle. Of course, they've been online with the Roadster and the Model X and the Model S for some years, which are over 100,000. And these are so popular that they have I think they have like almost 500,000 orders, and they're only producing maybe a few hundred per month. So they actually have to up their gigafactories to produce it. But they've sort of captured the imagination of the cool, sleek iPhone of cars, and that's sort of driving the market. I won't have one anytime soon. I certainly won't have the BMW anytime soon. But again, very impressive. What might be more your speed? This is the Nissan Leaf. This is a concept car of the new Nissan Leaf. I can't remember what they called it. SV. And the ones that you see on the road right now have a range. I think it's over 100 miles, I think, something like that. They don't look nearly as cool as this one, but they do have the greatest market share. They have pretty good resale value. And then, of course, the one that they're saying is sort of the Tesla killer, which is also one of the best reviewed cars, is the Chevy Bolt, not to be confused with the Volt, which is their combustion plus lithium-ion battery, but this is a pure plug-in. And so what you're starting to see in the last couple of years is because big countries like China or big municipalities like London are putting restrictions on combustion engines, somebody's got to create vehicles for these markets, even if the United States is sort of a laggard. So this is actually a list of all of the international car manufacturers that have at least one electric model in production. I thought it was really impressive when I saw it. Then I realized I don't know half of those companies, so I don't know what the Quantu is and so forth. But in fact, I believe GM just announced that they're going to have a whole plan to move to purely electric vehicles. Isn't that right? In the next couple decades. So there's the trajectory for electric cars in the United States. Yeah, so here's one example. China is making a timetable to basically ban all petrol and diesel cars, and Beijing is going to phase out taxis. So there's going to be new restrictions. I believe it's in Paris. They have restrictions during certain times of the day. You can't take combustion engines past a certain boundary within the city limits. India's trying to get all electric cars by 2030. And this is just a quick list of countries that have now said they're going to, at least, and they have announced, and they're targeting a phase out of fossil fuel vehicles by a certain amount of time. So if you're a car manufacturer and you don't have an electric vehicle car and you're in business in 2030, you may not be able to sell like a car in India, for example. So these are exciting developments. That's a misplaced slide, but solar panels sure are pretty. And also, actually, maybe that wasn't that misplaced, but people do know, like, just because you have an electric vehicle does not necessarily mean that vehicle is clean. It depends completely upon what the source of energy that your utility is providing. So in my case, I don't have an electric vehicle. That's an aspiration I have. But if I bought one, I didn't want my provider's Dominion, and most of their energy comes from natural gas and old fossil fuel sources, a little bit of renewables. But that just means I'm driving a clean vehicle with dirty electricity inside. So that's the link between the solar and electric vehicle and the lithium-ion batteries. But there's enough solar energy reaching the Earth every day and pure potential to fill all the world's energy needs for a full year. We just got to figure out how to capture that. In terms of jobs, right now, 9.8 million people globally work directly in the renewable energy sector, mostly wind turbine technicians, and whether they're installers or service technicians, and of course solar manufacturers and solar installers. 2.6 million jobs in the US in those sectors. And those are big. Wind turbine service technician is forecast to be the fastest growing job category. It says through 2024. I think a report came out last week that also said solar and wind are going to be the fastest growing jobs. And right now, we're approaching 1 million renewable energy jobs in the US. And in terms of jobs in the energy sector, as much as the current president wants to bring back older industries, the market forces really aren't going to allow that. And so a lot of the new energy jobs, they're just going to come from solar wind for all the economic forces that I've been describing to you. So in terms of new electric generation in the US as of last year, wind and solar are doing surprisingly well vis-a-vis natural gas. And as you can see, coal, not only are coal plants not coming online, but many are being shuttered or shut down because, regardless of policy, the market forces simply will not allow a return to coal. In addition, the business community is taking leadership. Companies like Starbucks, Microsoft, and REI and Apple are all announced, I think Google as well, targets for 100% renewable energy. And in fact, surprisingly, in the state of Virginia, Dominion's a bit slow in providing renewable energy choices for its customers. But when large companies, tech companies that need data centers, like Google and Amazon are looking to put up a data center, they do tend to bend over backwards because the businesses are actually determining the market, and they're starting to have certain standards of what their expectations are for their energy mix. In the U.S., solar energy jobs growing 17 times faster than the overall economy. This is just a quick overview, just to put a nail in the coffin, as it were, for coal. And again, we should still it's not funny when people are disenfranchised, when people are displaced, and their towns go belly up because the energy that has provided jobs and security for those families have suddenly disappeared, and there's not an alternative. We need policy at the national and state level to provide training for people who are in these industries to have a livelihood, and not to be politically frustrated, but to actually see a pathway toward being part of this new future that we're having. These were new plants that were proposed in the United States that aren't going to get built, defeated. These are existing plants that are going to be shut down. And these are ones that are announced to be shut down. Which basically means in the United States, coal, and this is a great thing because coal is one of the biggest contributor to the type of carbon gases that are causing these problems that we have. Natural gas, it is still fossil fuels. It certainly is cleaner, but it is not a clean fuel. It is a cleaner fuel vis-a-vis coal and oil. And even though during the Obama administration it was seen as a bridge fuel, we actually don't need as long of a bridge as we think, with all of these economic changes that we're seeing. And so hopefully natural gas is something that provides energy security, but isn't something that we then become reliant upon the way that we did coal, because we've actually turned a corner on coal, which means a cleaner atmosphere. And that's coal use for electricity generation. And that's how much coal companies are worth today, 87% of what they were worth back in 2010. The market has spoken. Now this is hopeful. I've actually heard something this week that makes it less hopeful, but what we've been seeing in the last 3 years is actually in a non-recession time, the first time, if you see right here in 2009, there's a dip in our carbon output, but a lot of that was the result of the Great Recession, the global financial crisis. But we're actually seeing a leveling off of some carbon dioxide for 3 years in a row, which is the first time in 40 years that has happened. I'm pretty sure I just read this week, though, that we've seen a 2% uptick as of the data this year. So, and also for us to stay under 1.5 and for us to meet these goals, and I think you've seen charts all day on this, we actually need to not flatten, but we need a dramatic reduction and change in the opposite direction. Same thing has happened in terms of U.S. greenhouse gas emissions. And a lot of that has to do with efficiency and, of course, all of these new things coming online. And, of course, we have the Paris Agreement. At the time, we were a signatory, one of the driving agents of doing that. Of course, we are now still part of the Paris Agreement, but the current administration has announced its intention to, running too long on time? Sure. So let me run through some quick things real quick, and then we'll leave it open for questions, yes, or no? Okay, sorry. Well, yeah, so let me just talk about then, to wrap up, what some challenges we have regarding the Paris Agreement. So the good news is there is a framework and there's an aspirational goal, and now the process is actually putting some teeth into it and making sure there's justice where some of the richer nations are providing mitigation funds and adaptation funds for some of the poorer nations. And the goal is to get us to stay definitively under 1.5 degrees Celsius. I already went over some of the challenges. But the good news was after the announcement of that, lots of leaders actually announced that they were going to stay and aspire to have those renewable energy goals. And it's cities and counties and mayors from all over the United States. So from a certain perspective, the United States is actually still in the Paris Agreement and committing to reductions regardless of what the federal government decides to do. So 125 cities, 9 states, 183 colleges. So I'm going to stop there. Sorry I went long. I should have had a timer. But basically the point of the presentation here, and if you would like to get a presentation in your community, in your church, your university, your class, you can just go to Climate Reality Project, to the Leadership Corps, and just request one. That's how I ended up here. You can find out a lot of the solutions and how to get involved. You can become a leader yourself and speak and find out how there are positive things you can do in your personal life and also in your community to actually keep this momentum going, because there's actually a lot to be hopeful about, and there's a lot of minds being changed about our climate challenges and our climate solutions. So thank you very much.